Hello, everyone, and welcome back. In the past few lectures, we've been defining and deriving all kinds of new functions. Some we may have seen before, such as the exponential or logarithmic function, but some of them might be entirely new to you, such as those hyperbolic trigonometric functions. Now, as we progress through this course and we start learning new functions and start working with new functions, it's important that we have some sort of intuition for how these things behave. And one metric for understanding how functions behave is understanding their growth. That is, what happens to the function as x goes to infinity. And in particular, what we would like to do is we would like to compare growth rates among different functions. You may have heard me mention in this class, in some of the videos, things like exponentials grow faster than any polynomial. Or I said in the previous videos about hyperbolic trigonometric functions that as x goes to infinity, say the exponential term e to the x dominates the exponential term e to the minus x. And so I use this in the sketching to say the function should look like, I don't know, e to the x or something like that. The question is, how do we know this? How do we quantify this mathematically? How do I know that the hyperbolic cosine function, so cosh of x, looks like e to the x over 2 as x goes to infinity? How do I know that it has an exponential growth rate? These are the questions that we're going to address today and quantify explicitly from a mathematical perspective using limits. Now, let me start with an example right off the bat. And let's imagine that I give you the function, say, y is equal to e to the x. And imagine that on my board here, I've drawn out the axes so that x is measured in centimeters. So imagine this is perfectly realistic, and y is also measured in centimeters. Now we have this rough idea that an exponential function looks something like this. But the question is, have we ever really stopped to think about how fast this growth actually is? And so what we can do is we can actually put in some values of x here and ask ourselves, what does this function actually look like? So first thing, if x is equal to 1, then approximately e to the x is 2.718, something along those lines. So let's say about 3 centimeters, just so that we can round this so we can get an idea, right? So pull out your ruler right now and look at 3 centimeters. I went over 1 centimeter and up about 3. Okay, that's not that big yet. How about at x equal to 6? So I move 6 centimeters along the x-axis. And in this case, e to the 6 is at 403 centimeters. So that's approximately 4 meters. Right? So I'm doing some rounding here. I'm just trying to give you perspective. But think about it. What's the height of the room that you're standing in? Currently, from floor to ceiling in the room that I'm in, it's maybe a little over 2 meters or a little under 2 meters, somewhere in that 2 meter range. So already, I'm not drawing this thing on the board because I've doubled the height of the room that I'm in already. And that's only going 6 centimeters over on the horizontal axis. Okay, so how about, say, x equal to 10? Well, in this case, e to the 10 is about 22,026 centimeters, which is about 220 meters. Now, I just looked this up before the video, and at the time of recording this, the tallest building in the world is the Burj Khalifa. It's about 820 some meters tall. So we're talking, if I went 10 centimeters on the x-axis, I am going more than a quarter way up the Burj Khalifa for this function e to the x. Now, finally, 2 more. I'm not even going to put the numbers in, but if I take x equal to 24, now I'm more than halfway to the moon. Okay, so all I had to do is 24 centimeters, less than a quarter of a meter along the x-axis, and I'm halfway to the moon. And finally, if I take x equal to 43, less than half of a meter, this graph, technically, if I could just, keep drawing straight up vertically, this is high enough to reach past the sun's closest stellar neighbor, right? So we're going all the way to Proxima Centauri to get to this thing, if I could imagine, drawing that. So that's ridiculous, right? For example, if you want to compare this, compare it with the growth rates of, say, y equal to x. Now that's easy, right? 43 centimeters over, 43 centimeters up. Or maybe y equal to x squared. This is about 1600 here. So 1600 centimeters. That's about 16 meters. That's we passed that after x equal to 10. Right? So these exponential functions, they grow extremely, extremely, extremely fast. Now think about the relationship here too. The x-axis is growing slow and the y-axis is growing fast. Now we've seen that the natural logarithm is the inverse of this function. So the natural logarithm has the opposite property. The x-axis grows fast and the y-axis grows slow. For example, it would take you, so if you consider y equal to the ln of x, and you want to ask, when is y greater than or equal to 43? For example. Well, in this case, it's 5 light years. Okay, that is ridiculously far. So this is a much slower function. Logarithms grow slower than any polynomials, and exponentials grow faster than any polynomials. Now, how is it that I can say that? How can I quantify that? How is it that I knew that that's the case? Well, let me give you a definition. We have a precise mathematical way of telling each other how fast functions grow. So let's say, let f of x and g of x be positive for sufficiently large x. So beyond some point, they're both positive, okay, for the rest of the x values. Okay, then we say f, maybe we'll put the definition in red. We say f grows faster than g, as x goes to infinity, if the limit as x goes to infinity of f of x divided by g of x equals to infinity. Right? So the numerator of this quotient is growing faster than the denominator, and so it's pulling it up to infinity. And so, or equivalently, if you invert that fraction, then you would get the limit as x goes to infinity of g of x over f of x is equal to 0. In this case, the denominator is sinking the function and it's pulling you down to 0. We can equivalently say, so we can also say g grows slower than f as x goes to infinity. So both of those things are perfectly valid to say. They mean exactly the same thing. They can be quantified using those limits. Well, then the question is, what happens? We've seen the limit is either 0 or infinity. There's a lot of numbers in between 0 and infinity. What happens if our limit lands on one of those numbers? Well, in that case, we say that f and g, they grow at the same rate. As x goes to infinity, I need to be precise here. We're always talking about as x goes to infinity. if the limit as x goes to infinity of f of x times g of x is equal to L, where 0 is less than L, which is less than infinity. So it's finite and it's positive. Okay, so that gives us a way of asking ourselves which functions grow faster or slower than other functions, and what functions grow at the same rate as x goes to infinity. Now, let's rhyme off a bunch of examples. Let me show you how I know that certain functions grow faster than other functions and that certain ones grow at the same rate. Let me start with an easy one. So let's take, for example 1, let's take f of x is equal to 2x and g of x is equal to x. Now, to the naive, maybe this would, maybe somebody would say that f of x grows faster because it's double what g of x is. But remember, growth depends on sort of derivatives here, right? And we're asking, how does this thing scale with x? And in both of these things, it scales linearly. So actually what we can see is that these functions grow at the same rate. Why? Well, if you look at the limit of their quotient, you get that the x's will cancel, so 2x over x, which is the limit as x goes to infinity of just the constant function 2, which is equal to 2. So f and g grow at the same rate. Now, for the remainder of this lecture, I'm always going to be talking about growth as x goes to infinity. So I'm not going to write as x goes to infinity every single time, okay? Just to save ourselves, just the annoying sort of notation every single time. Okay, let's take f of x equal to, say, e to the x, and g of x is equal to x squared. Now, I just told you at the beginning of this lecture that exponential functions grow faster than any polynomial. Now, how do we see it? Well, let's take some limits. Let's do e to the x over x squared. Now, this sort of leads to infinity over infinity. So the question is, what can we do? Well, we're back in the limits realm. So in this case, we've got an old tool, L'Hopital's rule, that can help us to simplify this thing, right? Remember, we can take the derivative of the top and the bottom for these improper limits. I like to denote that I'm using L'Hopital's rule with an L' R for L'Hopital's rule, L' HR for L'Hopital's rule after each equality, so that whoever's reading this can see what I've done. E to the x differentiates into itself. X squared differentiates into 2x. Now again, I've got infinity over infinity. I'm going to use L'Hopital's rule again. And so I get, again, e to the x on the top because it differentiates into itself. And now I have 2 on the bottom. And so in this case, I get infinity, which tells me f grows faster than g. And if you wanted to do that with, say, g is equal to x to the 10, you just have to use L'Hopital's rule 10 times. If it's x to the 100 million, L'Hopital's rule 100 million times. It gives you exactly the same thing as you go through it. Okay, let's continue with some examples. Here's another one. Let's say f of x is 3 to the power of x, and g of x is equal to 2 to the power of x. Now, if you think back to the very first example, I had 2x and x, and we saw they're both sort of linear functions, and it turned out that they grow at the same rate. So if I'm looking at this, I'm saying, well, they're both exponential functions. They probably both grow at the same rate. But if you plug this into the limit here, you get 3 to the x over 2 to the x, which is equal to you can put this as 3 over 2 all to the power of x. Now 3 over 2 is larger than 1. So now you've got another exponential function. You're taking something larger than n and successively adding more powers to it, or add 3 over 2 to the 10, 3 over 2 to the 100, 3 over 2 to the 1000. And this thing is going to infinity, which tells us that these exponential functions, the base matters, right? 3 over x grows faster than 2 to the x. And we can actually put this in general. You can say that f of x equal to a to the x grows faster than, g of x equal to b to the x when a is bigger than b, which is bigger than 1. Right? So now the base matters for these exponential functions. Okay, so how about the logarithms? I said to you at the beginning here that the logarithms grow slower than anything else. They're the slowest growing functions that we have a precise name for. So how do I see, for example, that maybe x squared grows faster than the natural logarithm? Well, let's plug this into our limit. Now we know that the logarithm goes to infinity as x goes to infinity. So again, we have an indefinite form here, so we can use L'Hopital's rule. And my personal favorite thing about the natural logarithm is that it differentiates into not exactly a polynomial, but something very similar, right? 1 over x. In terms of, for us who care about integrals in this class, it's pretty close to an integral, right? Or it's pretty close to a polynomial because now the integral rules are all the same. I know that it's not technically an integral or a polynomial, and people might take issue with that. But I like to think of the natural logarithm as getting close to a polynomial. So in this case, the x squared on the top differentiates down to 2x. And I get 1 over x on the bottom from the natural logarithm, which I can simplify out that fraction now. And I get 2x squared, which is equal to infinity, which tells me x squared grows faster than the natural logarithm of x. And in fact, you can do that for every single polynomial. That will still work if you use x cubed or x to the 5 over 3 or x to the 0.00001. Still going to work. Let me show you. Let me show you that if you take root functions. So let's take, say, f of x is equal to the natural logarithm, and g of x is the nth root function, x to the power of 1 over n. I'm going to show you, so for n, a positive integer, just so it's clear that this is actually the nth root. Well, then the logarithm is still slower than that. How? Okay, let's take a look at the limits here. Natural logarithm, x to the 1 over n. Again, we're going to use L'Hopital's rule. Again, I like to denote it for the reader. It's very nice if you can tell, or if you can guide the reader through your steps and your thought process here. And the nice thing, again, the natural logarithm goes down to something that can mingle with polynomials. Maybe that's a nice way to think of it. And I get 1 over n, x to the 1 over n minus 1 here now, which when I simplify out this fraction leaves me with n divided by x to the power of 1 over n, which now goes to 0 again as x goes to infinity, since n is a constant. It's fixed. It could be 3, it could be 5, it could be 100 billion. It's just a number. And so this tells us ln x grows slower than x to the 1 over n. So it's ridiculously slow how this thing goes. Okay, so the last one that I want to show you, the last example in this portion, if you think about what I did in example 3 here, I show you that the base matters when it comes to exponentials. Okay, so then, you're smart, you're thinking to yourself, then the base must matter when it comes to logarithms, right? And not quite, actually. So let me show you. Let's say, let's take a and b greater than 1, and let's take f of x equal to log base a of x, and g of x equal to log base b of x. And so we would expect, at least, based on some knowledge, that there should be some ordering happening here. If a is bigger than b, then f grows faster or slower, whatever it happens to be. But it turns out because of the change of base formula, that's never the case. So let's take a look at this. Log base a of x divided by log base b of x. Remember, we have the change of base formula that turns these things into the natural logarithm. So ln of x divided by ln a divided by ln of x divided by ln b. And the lns will cancel each other, leaving me with the limit of a constant function. Remember, a and b are fixed. They're not changing with x. So I get ln b divided by ln a, which is ln b over ln a. And since b is bigger than 1, this thing is never 0. So this tells me that log a of x and log b of x grow at the same rate. So that's kind of weird, right? It's kind of interesting, kind of a strange property, but there it is, right? There's the proof right on the page. So it's got to be true, even if it might not be as intuitive as we might have hoped it would be. Okay, let me show you another nice little property of this. So let's say, suppose f and g grow at the same rate as x goes to infinity, and g and h grow at the same rate. As x goes to infinity. So that is, so I have that the limit as x goes to infinity of f of x divided by g of x is equal to some limit L1. And the limit as x goes to infinity of g of x divided by h of x is equal to L2. Then we can find that f and h have to grow at the same rate as well, right? So this is a transitive property. If f and g are related and g and h are related, then f and h have to be related too. And this is actually just a pretty simple little manipulation here. I can take that fraction and I can multiply and divide by g. So I get f of x over g of x times g of x over h of x. And if I want to, I can break up the limit here. So I get the piece that's equal to L1 and the piece that's equal to L2. Which is equal to L1 times L2. So this shows that f and h grow at the same rate too. Right, so log base A and log base B grow at the same rate. Log base B and log base C grow at the same rate, and therefore log base A and log base C grow at the same rate. Okay, why is this useful? Let me give you an example. Let's let f of x equal to the square root of x squared plus 5 and g of x equal to 2 root x minus 1 squared. I'm going to show that these things grow at the same rate. Now, if you set up your limit, it's going to be a huge pain to simplify. Look at how ugly things are. If you want to set up that limit, you're going to have a square root divided by something. You know, it's just going to be brutal. But what you can do is you can compare them both to different or to the same function. And we can compare them once we show that they both grow at the same rate as that common function. Then we can use the property that I just showed you above to show that these two functions grow at the same rate as well. So what I'm going to do is I'm going to compare them to x. Now, how do I know to compare them to x? Well, take a look at the first function here. Basically, what's happening is x is getting big, so x squared is getting big. X squared plus 5 is big too, but we don't really care about the 5. Imagine buying a home for whatever, $1 million. And somebody says, you throw in another $5 and I'll do this, right? I'll give you this. You go, yeah, I just spent $1 million. Sure. $5 means nothing to me right now. So that's what's happening. So as x gets big, this thing really is just x squared. And then you're taking the square root of it, which is basically x. So let's do that. Let's compare that original function to x. What I can do here is I can multiply the top and the bottom by 1 over x, and I can pull the 1 over x on the top into the square root. So I get 1 plus 5 over x squared, because when it went into the square root, it becomes squared. So 1 over x, and then into the square root becomes 1 over x squared. And now I have x times 1 over x, which leaves me with the square root of 1 plus 5 over x squared. Now, as x gets big, 5 over x squared goes to 0. And this essentially leaves me with 1. Then, now that we've compared f to x, let's compare g to x. So I get 2 square root of x minus 1 over all squared. And in this case, what I can do is I can absorb the x into the square term. So I can think of this as 2 root x minus 1 over the square root of x, all squared. Right? That's just squaring the square root in the denominator. And now I can distribute out this quotient, leaving me with 2 minus 1 over the square root of x, all squared. Now that square root of x, 1 over the square root of x, that's going to 0. And so I get 2 squared, which is equal to 4. And so I can see that both f and g compare to x. They grow at the same rate as x. And therefore, since they grow at the same rate as a common function, they grow at the same rate together. Okay, now if you've taken any computer classes, maybe you've seen a notation used for these growth notations. And that's what's referred to as big O and little o notation. So let me give you an example, or let me give you the definition here, and then we can talk about it a little bit. So a function f is, let's put this in red. It's of smaller order than g. So the O in big O stands for order as x goes to infinity. If the limit as x goes to infinity of f of x over g of x is equal to 0. Okay, so that just means that it grows slower f grows slower than g. And so we write, or we indicate this by writing f is equal to little o of g. And you literally pronounce it the way I just pronounced it. F is little o of g, little order. You can think of it like that. So what are some examples? Well, one example might be that the logarithm is little o of x as x goes to infinity, because we've already seen that the limit as x goes to infinity of ln of x over x is equal to 0. Actually, we didn't see that. We saw it with x squared, but it's the same proof. You can use L'Hopital's rule to get that again. Another example of this is that x squared is little o of x cubed plus 1 as x goes to infinity. And this is because in the limit here, your numerator has a lower degree than your denominator. And so this thing is also going to go to 0. Okay, so this allows us to talk about the two cases where you have growth that is faster or slower between two functions. Then what happens if you have growth that is equal to the growth of another function? Let's look at a definition again. Okay, so let f and g be positive for sufficiently large x. Then f is, in this case, of at most the order of g. As x goes to infinity. If there is some number m greater than 0 for which f of x over g of x is less than or equal to m for sufficiently large x. Okay, so if you can bound the quotient of those two functions, then these two things are going to be of at most, f will be of at most the order of g. And we indicate this by writing f is equal to big O of g. And again, you say it out loud by saying big O of g. It's the same idea as little o, except this one is allowing you to grow at the same rate. Remember, little o says that you grow at a strictly slower rate. F is slower than g, or a lower rate. Big O encapsulates everything that little o has, but it also allows you to go up to the same rate as. So let me give you some examples. Example 1, x plus sine of x is equal to big O of x as x goes to infinity. And this is because x plus sine x divided by x is less than or equal to 2 for all x greater than or equal to 1. So if I look at x larger than or equal to 1, then I guarantee that that thing is bounded. And so the definition said that I just need to have, for some sufficiently large x, so that's x beyond some point, that the quotient is bounded. In this case, it works for every x bigger than 1. okay, e to the x plus x squared is big O of e to the x as x goes to the infinity. And this is because the quotient e to the x plus x squared over e to the x approaches 1 as x goes to infinity. So because that limit exists, then definitely this thing is going to be bounded, right? You can find x large enough where this quotient is less than 2, because eventually it's getting really, really close to 1. And then finally, I'm going to try and squeeze it in here. I somewhat apologize, but I don't want to start a new page. X is big O of e to the x as x goes to infinity. And this is quite easy to see in the same realm. This comes from the fact that x divided by e to the x goes to 0. Just use L'Hopital's rule as x goes to infinity. So it's the same idea. This thing, the limit is finite. That's one way that you can show that things are big O of each other, right? So as long as the limit is not infinite, you're good, right? These things, that tells you that f is at most the order of g. Okay, so in this lecture, we got to see how we can compare the growth rates of functions as x gets really large. What we've seen is that exponential functions grow faster than any polynomials, and you can prove that with L'Hopital's rule. And exponential functions with different bases behave differently. They have different growth rates. Whereas logarithmic functions, they grow slower than any polynomial. Again, just use L'Hopital's rule to show this. And what was sort of interesting is we saw that logarithmic functions with different bases still grow at the same rate. And that is a ridiculously slow rate. And then what I showed you is that we have a way of actually writing how these functions compare to each other using little o and big O notation. Now, as I mentioned, if you came to this lecture from a computer science background, you probably are familiar with big O and little o notation. And that's because we use big O and little o notation quite frequently in computer science to denote how an algorithm scales. So this is something that is extremely important outside of calculus that I'm not going to get into too much in this class, but I'd be happy to talk to you about. But for this class, we're going to use those big O and little o notations just so that we can process these functions, so we can understand, how these things look beyond the little tiny area that we can kind of graph these things in.